In this video, we're going to look at exponential equations, and we're going to solve the three main types of exponential equations, but we're also going to look at some exponential inequalities. Okay? So to start, I want to briefly describe the different types of equations that you're going to see and how to approach solving them. One of the things that I find most students have difficulty with is identifying which type of equation they're looking at. Most students, when they get an exponential, they just try to solve it. But it really is beneficial to determine which type it is and use the methods that are useful for that type of problem. Okay? So there's three forms. The first is if I have similar bases. So if I'm looking at something of the form a to the x equaling a to the y. And before I keep going with that, I want to say, I say similar bases because it doesn't necessarily need to start this way. But if I can simplify it down so that the bases are the same, then solving is very nice because I can solve it directly. If a to the x equals a to the y, then x has to equal y. So I can basically just look at the exponents and solve the exponents equal to each other. Okay? If I have different bases, then it becomes a little bit more complicated. And the idea here is if there is really no way to simplify them down, then I need to use inverses to get rid of the exponentials. Another way to think of it is to use the property taking the log so that I can bring the powers down front. And so what we would do is we would pick a base, and the base could be picked based on the bases currently in the problem, or depending on how we want to write the answer. So if my answer needs to be in terms of natural logs or common logs, then I'll use that base. But basically here what we're going to do is we're going to take the log of both sides, and I'm just going to call it log base c, because you can pick what the log is. And the reason that's useful is because then I can bring that power down on both sides and solve the resulting equation. And it doesn't look pretty here, but the reason this is nice is because log base c of a and log base c of b are just numbers. And all of my variables are now out of the exponent, and it goes back to solving a linear, a quadratic, a rational, or a radical equation. Things we've done well before this. Okay. Other types are our quadratics, rationals, etc. And what this means is I'm not just looking at two expressions that are equal to each other. I'm now going back to actual equations of those types of forms. So for example, I could have something that looks like something like this. This is an exponential equation. It doesn't follow either the other two types because I have pluses and minus signs, which gives me three terms instead of just the two. And so here we would use other methods like our quadratics, how we solved them, either factoring or quadratic formula, solving rational equations, so maybe I have a fraction that has my exponentials in it. But for these types, they don't quite follow these, and I would have to go back to methods we've talked about in prior sections. Okay. And then, like I said, we'll look at some exponential inequalities. And for these, we're going to use a lot of the same properties we use here. The only difference is we'll be solving inequalities. So a lot like our quadratic inequalities or our rational, once we find those boundary points, then we'll take those boundary points and put them on a number line, and then find the regions that work and get our solution. Okay, so there's just an extra added step for those inequalities. Okay, so let's start with a couple of equations, and for these we're going to start with the ones with similar bases. And so I've put up two types here because in some cases you'll get ones that are very straightforward. You can tell just by looking at them that the bases are the same. And then there's the ones where you have to do a little bit of work to get the bases to be the same. Both of these are solved very directly. Okay? So let's start with this one. 5 to the 2x equals 5 to the x minus 1. here I can clearly see that the bases are exactly the same. And so in this case, because they're the same, I can just equate the exponents. So this tells me that 2x has to equal x minus 1. And now I'm back to a linear equation. So x will equal negative 1. Okay? And that's it. I'm done. Okay? If my bases are the same, that's as far as I need to go. It makes it very easy to solve. If they're similar, so if they're not quite the same, but they're similar, there's only an extra step I need to do, and that's to rewrite them so that the bases are the same. Now, how you do that is up to you. My suggestion is to go back to the smallest base that's common in both of them. Okay? So in this example, 4 to the x plus 3 equaling 8 to the x minus 2, 4 and 8 aren't quite the same, but I can think of 4 as 2 squared and 8 as 2 cubed. So I can rewrite my expression. Remember, power to a power, so this is going to be a 2x plus 6 equals 2 to the 3x minus 6. Okay, so I start by getting them back to what we had over here, where the bases are exactly the same. And now I can equate my exponents. So 2x plus 6 has to equal 3x minus 6, and now I can just solve. So I'll subtract 2x and add the 6, and so x has to equal 12. Okay? Now, like I said, sometimes people don't always look at this, and they'll use the logarithms to solve, which is fine. You will eventually get the same answer. The problem is, it doesn't simplify directly if you use the logarithms. You actually have to realize you need to simplify further, and it's a lot more steps than this. So next, let's look at some examples of solving exponential equations that have different bases. And again, just like with the same bases or similar bases, I'm giving you a couple different ones that we want to look at because they do have some differences in how they're set up. Okay? So in this first case, this is what I would consider probably one of the simplest forms, where I have an exponential expression equaling just a number. Okay? Or you can think the other side of the has an exponent of just 1. Okay? In this case, let's say we want to have our solution so that it is in terms of common logs. Okay. Again, for some of these, you may be asked to get a decimal approximation. Start by picking which logarithm base you want, because you're going to need to use logarithms to solve these equations. And decide that at the beginning, because like I said, you have to be consistent all the way through. Okay. So in this case, if I'm going to use common logs, I'm going to go ahead and take the log of both sides. And all that does for me is, by my property, I can bring that x minus 1 down in the front. Okay. Now again, it's still an equation and I'm trying to solve for x, so I want to isolate my x term. Now to do that, and this is again where some people kind of go error-y on this, I want to start by distributing so that I can get the x term by itself over here. So remember, log of 3 is just a number. And now I can get my x term by itself by moving that log 3 to the other side. Okay. Your properties will come into play here. So my x log 3 will equal log of 15. So again, remember, adding, I can multiply the arguments. And so x will equal log of 15 over log 3. Okay. Remember, I need the logs in both the top and bottom. Those do not cancel out. Log is a function. It has to have an argument. Okay, so you can't just cross those logs out. That does mean something different than log of 15 over 3. Okay, so make sure you're writing this correctly. Okay, here would be my solution. As far as an exam goes, that's a full credit answer right there. If I'm on the homework and it asks me for a decimal approximation, then you want to take this a step further and plug this in and get your decimal. Okay. All right. Let's look at the second one. So 2 to the 5x minus 1 equaling 6 to the x plus 1. It's the same type of problem. The difference now is I have x in both exponents. Okay? For this one, let's look at this in terms of the natural log. And I know that makes sense, so let me write it this way, in terms of ln. Okay? The process you'll see is very similar to what we just did. The only main difference is I'm using a natural log instead of a common log. Okay? So here, again, because I can't get the bases the same, I'm going to start by taking the natural log of both sides. Okay? Again, I can use my property to bring the powers down to a coefficient. And again, when I do that, notice I'm putting these in parentheses. And that's because, again, I need to multiply that natural log of 2 by both terms, and same thing with the natural log of 6. Again, a common error. People will leave this off and they'll think 5x minus ln of 2, and then they'll try and solve, and they wonder why things go wrong. And that's because you need to have those parentheses there. That distributes. Okay? Which is going to be our next step, because we need to get, again, the x's on one side of the equation. And at this point, I can't do that because the x is attached to both natural logs. So we'll go ahead and distribute. Now we can move all the x's to one side of the equation. And it doesn't matter which way you move it, just like with the equations we did before. You just have to watch your signs and be consistent. Okay? On the left side here, again, I have x's in both terms. I want to get x by itself, so I'm going to need to factor that x out. And then on the right side, again, I can use my properties and go ahead and combine that. So again, the addition will turn into a multiplication. If you want to go ahead and combine here, you can. Most of the problems that you're going to see, these are going to have a coefficient on one of them. So if you want to leave it as a difference or sum on the other side, that's fine. If you have coefficients over here, you can leave it separated. Okay? So now I'm just going to solve for my x by dividing out. And again, that's full credit. I don't need to take that further unless it specifically states to put it in a decimal form. Okay? Again, if this one had asked for a common log, the process is exactly the same. The only difference is I'm going to have a log in there instead of an ln. Okay? Alright, for this one, let's say we want to round the answer to 3 decimals. Okay? Now, this one, the reason I said that is because it doesn't tell you which logarithm you need to use. But if I look at my equation, it kind of tells me which logarithm I'm going to want to use, because I need to be able to get a decimal approximation. Now I can do it with other logs, but in this case, because I have an e in here, I'm probably going to want to use the natural log, because then things will cancel out a little nicer than they would with, say, a common log or a log base 5 or any other log. Okay? Here again, e and 7, I can see my bases are not the same and can't be written the same. So I'm going to go ahead and take my natural log of both sides. Okay? And again, the reason I chose natural log in this case is because I have that e in there. So when I look at this side, the natural log of e will cancel out, and I'm just going to get the 3x minus 1. Okay. Just like the previous examples, I want to go ahead and get the x's all in one side. Okay. Again, it doesn't matter which way you move them. I like my x's on the left, but you can certainly do it on the right. So here I would say 3x minus 2x ln of 7 will equal 1. Okay. Again, I'm going to factor my x out. And then I'm going to divide out by x, the 3 minus 2 ln of 7. Now at this point, again, we're going to plug into the calculator. Again, you've got to be careful how you plug this in. You're definitely going to need some parentheses. So 1 divided by that group, and then do your 2 ln of 7 in there, however that calculator requires you do that. And when I do that, I'm going to get negative 1.121. Okay? And again, the approximate symbol because I'm rounding, and it's not an exact answer. For this next part, we're going to look at some of the other types of equations that you're going to see. And like I said, some of them will revert back to different forms that we talked about in prior sections. Things like solving quadratic equations, solving rational equations, factoring, things like that. The key to knowing how to use the different methods here depends on what your equation looks like. So again, if I can't simplify it down to an exponential equaling an exponential, I know that I'm looking at another type of equation. Okay? So in this first example, we're looking at e to the 2x minus 3e to the x plus 2 equals 0. Okay? The first clue here that I'm not looking at one or the other, meaning similar bases or different bases, is because I have 3 terms. Okay? If I have 3 or more terms, I cannot use the methods we described previously. Okay? So here, the thing to notice is with my 3 terms, I notice that I've got the same base in my exponential equations, and I have a constant term. Okay? And if I look more closely at those like base terms, I can see that I have twice the power on one of them than the other. Okay? So this is actually a quadratic form. Okay? And so what that means is I want to use some quadratic methods to solve. Now I can do that directly, but for some people it's hard to see the quadratic in here. So I would suggest rewriting it. I'm going to let, say, w equal e to the x. Okay? I'm always going to pick a different variable, and I'm going to always let it be that second one, the smaller power of the exponential. Okay? And if I do that, I can rewrite my equation, and we can see it's going to be w squared minus 3w plus 2 equaling 0. Okay? So just substituting in. And from there, well, it's a quadratic equation. So at this point, it's just a matter of factoring. Or if I can't factor, using my quadratic formula. So here I can see w minus 2, w minus 1. So w will equal 2, or w will equal 1. Okay? Not done. So here I'm solved for w. I need to solve for x. So at this point, I'm going to plug back in e to the x is equal to 2, or e to the x is equal to 1. Okay? And for these, now I am back to those other type of equations that we talked about. In this case, I have 2 terms, and in this, I can't get the bases to be the same. So I'm going to solve by taking the natural log of both sides. Okay, so on the left here we get x is equal to the natural log of 2. Over here I'm going to do the same thing, so ln of e to the x will equal ln of 1. Here x will equal, and remember your properties, ln of 1 is 0. Okay, So in this case, there's two solutions for my equation. Okay. In the second example, we're almost looking at something similar. Now, in this one, it's a little difficult because I do have two terms. The main difference here is my two terms, and one of them, my variable is in both the base and in the exponent. Okay? So here that x is both in the base of an expression as well as the exponent of an expression. So that's what tells me in this case I can't do the things I did in the prior, meaning similar bases or different bases. Okay? Here, I want to look at the equation, and the first thing I notice is there's a 2 to the x in both of my terms. Okay? So here, I'm actually going to factor. Okay, so I'm going to factor out a 2 to the x, and we'll get an x squared minus 1 equals 0. And now I can solve. I've got my zero product property. So this says that 2 to the x equals 0, or x squared minus 1 equals 0. Okay, this one goes back to prior stuff. So x squared will equal 1, x equals plus or minus 1. Okay. Over here, this goes back to our different bases. So 2 to the x being 0, well, I'm going to take natural log of both sides. Again, you can pick your base, so if you don't like ln, you can use log or ln log base 2, whatever. Okay. Now here, I'm going to pause because there's a couple of things to mention here. First off, if you noticed that 2 to the x can never equal 0. So if you remember all of your properties from graphs and things like that, you can stop here and just say no solution. If you didn't recognize that, you can go ahead and do the natural log. And so you'll see here ln of 2 to the x equals ln of 0. If we try solving this, you notice if you tried plugging ln of 0 into a calculator, you get an error message. And again, remember that your natural log function, the domain for that is strictly positive, meaning it can't equal 0. Okay? So in this case, there's no solution for that part of it. Okay? So here, for this one, the only solutions we have are x equal plus or minus 1. Okay? Alright, so let's look at one last example over here, and that is 10 divided by 1 plus e to the negative x equaling 2. We want to solve this equation for x. Okay, so this is a rational equation. And for the rational equations, what we did was we started by looking at the LCD, multiplying both sides by the LCD to get rid of the fractions. Okay, here it doesn't matter that I have an exponential in here. I'm going to do the same thing. So we're going to start by taking our LCD, which in this case is 1 plus e to the negative x, and we're going to multiply both sides by that. Okay. From there, we can go ahead and distribute. And notice at this point we get some like terms. So we can subtract 2, 8 will equal 2e to the negative x. Okay. At this point, I don't want to quite take my natural logs yet. Okay. And that's because I've got this coefficient on my exponent. Okay. So here I want to divide out first so that I get the exponent by itself. Okay. And then from there, now I can take the natural log of both sides. So the ln of 4 will equal the ln of e to the negative x. Okay. Again, the ln and e will cancel out, so negative x will equal the natural log of 4. And then getting x by itself, we'll divide by a negative 1. So there would be our solution. Okay. So there's some other types of equations. And again, they're all going to be a little different depending on what your setup is for them. But again, once you've figured out what the setup looks like, whether it's a quadratic, a linear, a rational, or something you can just factor, once you set that up, Eventually, you'll get back to the things we were talking about in the prior sections, where we're looking at solving the exponential equations of similar bases or different bases. The last part of this section, we're going to look at the exponential inequalities. And again, these are very similar to what we saw with the exponential equations of similar bases and different bases, as well as some of the ones that were in the other category. The idea for these is very similar to inequalities in general. The first thing I want to do is try solving the equation and then solve for where the region is included and not included. Okay? And that usually means looking at a number line and figuring out which points within the number line are part of the solution region. So, in this first one, 2 to the 3x less than 34. Well, again, I'm going to start by solving it as an equation, meaning I need to find the boundary points. In this case, if I look at it as an equation, I have different bases. So again, I'm going to start by solving with the different base methods. Here again, I'm going to use natural log, but again, you're able to use whatever base you want on your logarithm. Okay, so I'm going to rewrite this, ln of 2 to the 3x, and again, I'm looking at the equality. I know it doesn't equal that, but I'm going to start there so I can get my boundary points. Okay, from there I can bring my exponent down and solve for x by dividing out. Okay, so there's my boundary point for the inequality. Okay. Now, before I can go further, I need to know approximately where that is on the number line. So if I plug this into a calculator, we get about 1.6958. Okay? So if I'm looking at ln of 34 over 3 ln of 2, I know some good test points would be something less than 1. So I'm going to try 0. And then something bigger than the 1.69. So I'm going to say 2. Okay, those are the two test points I'm going to try. And so if I plug these back into my original function, I just want to see if I get something bigger or less than 34. So we can see if I plug 0 in here, I get 2 to the 0, which is just 1. 1 is less than 34, so that's true. And if I plug in 2, I'm getting 6. 2 to the 6 is 64, which is not less than 34, so that one's false. Okay. Now to get my solution, remember your strict inequalities give us open circles, and for our solution we want the true region, so we're going to shade to the left of that. Okay. Now exponentials, remember the domain is all real numbers, so this truly does go to negative infinity. So our solution, x is going to be in the interval from negative infinity up to the natural log of 34 over 3 natural log of 2. And again, it's a parenthesis because we're not including that solution. Okay? Alright, let's look at our next one. So x squared e to the x minus 2 e to the x being less than or equal to 0. So again, we want to start by solving the equation. Okay, so if I'm looking at this, this is one of our other types because I have two terms, but again I've got my x in both the base and the exponent. So in this case, I'm going to factor. I'm going to pull out an e to the x, and I get x squared minus 2, and I want this to be equal to 0. So again, the equal is just so I can get the boundary points. Okay. So either the x has to equal 0 or x squared minus 2 has to equal 0. Again, if we think of our exponentials, we know that's never going to be true. So we're just looking over here at x squared equaling 2 or x equaling plus or minus root 2. Okay. Now again, I'm going to put these on a number line. Negative root 2 is over here. Positive root 2 is over here. Again, if you don't know the approximate value, you want to figure that out. But these are approximately plus or minus 1.4. Okay. So if I'm picking some test values, well, 0 is certainly between them. Something bigger, well, we can use 2. Something negative and less, we can use negative 2. Okay, and again, we're looking at an exponential function, so we again know that the domain is all real numbers. Okay, so now we're just going to test these by putting them back into the original. So if I plug a negative 2 in, we're looking at 4e to the negative 2 minus 2e to the negative 2. Well, that's 2e to the negative 2. I need to know if it's bigger than 0 or less than 0. Okay? Again, this is where your properties come in handy. E to the x, we know the base is bigger than 1, so it's increasing. But more importantly, the range is always positive. It's always 0 to infinity. So this value is greater than 0. Okay? So in terms of our equation, that's going to be false. If we plug in 0, we're going to get 0, e to the 0, which is still 0, minus 2e to the 0, which looks like negative 2. That is certainly going to be less than 0. So that one is true. And if we look at positive 2, we get 4e squared minus 2e squared, which looks like 2e squared. Again, the e is positive, 2 is positive, so that is going to be positive. Okay, so in terms of our solution, we want the true regions. Our inequality is inclusive, so I'm looking at the closed circles and everything between. Okay, so here our solution is going to be all x in the interval from negative root 2 to root 2. And again, we use the brackets because we're including those values. If I'm looking at this inequality, it's what we consider a bounded inequality. There's the function kind of between two bounds. I can solve this one piece at a time, or I can do it all together. And the reason I mention the one piece at a time is because in order to solve for the boundary points, I have to think of this as two terms where they are different bases. And again, same thing over here. It's two terms with different bases. So I'm going to need to use logarithms to solve. Okay? So here I can take the natural log of everything. So again, think all sides of the inequalities. And I'm actually going to start this over. So I'm going to take logs of all sides of the inequalities. And in this case, because I have 10 as my base on the exponent, I'm going to use a log base 10. So I'm going to take log of 2 less than log of 10 to the x less than or equal to log of 5. Okay, and nicely the middle piece there, log of 10, cancels out. So we're looking at log of 2 less than x less than or equal to log of 5. Okay, and the reason this one is nice is because that's it. There's my solution. Notice this one I didn't change it to equality because I really didn't need to. The way it's set up, I can solve it directly. And so there would be my solution. If I was going to put it in interval notation like we did the others, we would just say that x is going to be in the interval of log of 2, comma, log of 5. That side is going to be inclusive. Okay? And remember, these are just numbers. They're not pretty, but they're just numbers. But there would be our solution for that inequality.